Okay, my apologies for any noise that was on the other video. Working with a different microphone than I normally work with here, and I think it's picking up an electronic noise in the background when I turn it up too loud. So I'm going to talk loud and into the microphone, hopefully make this audible, but I've had to turn up the volume to be heard, because if I add any gain to this microphone, that high-pitched noise comes in. So hopefully this is audible here. I will move to my other equipment shortly. And if need be, fix any of these sound issues. What we're going to be looking at are equations. And equations are two sets of expressions separated by an equal sign. So we have an expression on one side and the other. The equal sign kind of takes the place of the word is, and we call this the left-hand side and the right-hand side. And those are the official mathematical terms for it, even though they don't sound that official or that deep. But we have the LHS and the RHS. And the equations link expressions into something that's generally called a statement. Now we'll find that we'll get other operators or other comparisons will get less than, greater than, less than, equal to, greater than, equal to, that we can also put in the middle. But with statements are either true or false. True or false. And so let's look at the statement I made here. I said 7x equals 35. We don't know the truth of this statement, right? The truth is ambiguous. But if we assume it's true, then we can manipulate this, because this quantity is equal to this quantity. So let's say I have 4 equals 4 as a quantity. Well, then in whatever I do to one side, I can do to another. And so I want to isolate the thing I don't know. We want to isolate the unknown thing. And I'll keep my Pemdas relationships over here. And I'll say, hey, I have a multiplication going on here, so I want to do the inverse of multiplication. I want to divide. So I will divide the left-hand side by 7. Because if I do that, 7 over 7 is 1, it will isolate the x. But because I'm assuming this quantity is equal to this quantity, to keep them equal, to keep the truth, whatever I do to one side, I have to do to the other. And so 7 over 7 is 1. That leaves me with x. And 35 over 7 is 5. And so we say I've solved the equation because I've used the truth, or the assumed truth of each side, to isolate the unknown thing. Now, this statement that comes out of this, I can say is as good as a truth. And if I plug it back into the original equation, so we can look at solving equations as being the way of finding all values of x that make the equation true. And there's going to be many different types of equations or formulas that we can look at. So the first equation type we're going to look at is called linear. And linear equations are such that we have one variable. Well, and I guess we're going to say we're going to look at linear equations in one variable. There are other ways we can talk about this. And so we have the one variable with no power. So it's, or we could say it's to the first power. And we'll find that we call the power of variable is the degree. And so this would be a first degree. And the number in front is just a multiplier towards that. And then there's also a constant. And we set it equal to 0. A hint at where we're going to this is eventually we will be able to map two variables to a plane, and a linear equation makes a line where the y value is equal to a slope times the x value plus where it crosses. And so there's where that's going to be the b value. And so when we set this equal to 0, we're saying we're looking for this point here. This point where this line intersects this x. And that's going to be a lot of what we're going to work towards, is making this visual representation for the quantities that go underneath. And so to start on our journey for that, we're going to look at linear equations in one variable. And in doing that, they have x to 1 power. And so what we want to do is we want to find all of the equations where it is true for whatever value of x we find. We're going to solve for x to find all values of x that keep the equation true. And these things are called the solutions or the roots. So to find 4x plus 12 equals 0, I want all values of x such that this is true. Well, and to do this now, we do what algebra was called, what the name algebra means. We reconcile disparagent parts. And here's a part, here's a part, and then here's a part. And they're disparagent because they're not in the same terms. They're different. But we're going to force things over. The general game is to get the variables on one side and the constants on another. And again, it's not a hard set fast rule, but we'll onion them like Shrek. And when we perform operations, we do work our way down Pemdas. When we solve equations, we tend to work our way back up. Though we can do some tricks with distribution to simplify things. So using this kind of reverse PEMDAS rule, I'm going to look at this 4x plus 12 and see what I can do to solve it. Find all values of x that keep it true. So I'm going to bring it down here. And I'm going to say, well, I need to get x on its own, and I'm going to start by reversing the additions. So to reverse the additions, I want to subtract 12. But whatever I do from one side, I do to the other. And so 12 minus 12 is 0. And 4x plus 0 is 4x. That's our identity coming into play. And this side is negative 12. And now I have a multiplication, and I need to reverse the multiplication. So I'm going to divide this side by 4. But whatever I do to one side, I have to do to the other. And so I have x is equal to negative 3. I can say my solution set is negative 3. That is all the values of x that keep this true. Well, let's check that. So to check it, I come back up above, and I now evaluate this equation with negative 3 in place of x. And so 4 times negative 3 is negative 12. Negative 12 plus 12 is 0. And so my statement says 0 is equal to 0, and this is true. So this value of 3 keeps my initial statement true when it is the solution set for x. And so we have this ability to solve by doing to one side whatever we do to the other. This is actually holds for many different types of mathematical problems, that whatever you do to one side, you do to the other. And a lot of mathematics is inventing things to do to one side of the equation. What we want to kind of think of in the end is all of this stuff represents a quantity, a number. And the statement is saying that whatever all the stuff represents, in the end, it's going to be 0. And the game is to find the x that makes that the case. And what I'm going to do here for this module, it's a little bit different, is I'm going to do a lot more examples, and I'm going to verge away from the text for a bit. We'll leave the text notes up, because I want to focus on the idea of whatever you do to one side, you do to the other. And instead of calling it the multiplication property of addition or of equality, or the addition property of equality, we're going to look at solving all of these things collectively. So I'm going to go through some of the odd problems in the textbook and see the solutions. What I want to do is I want to do one where we see what it means to not be true on all of these. So let's look at this one here. 2x plus 6 equals 2 times x plus 4. Now my game here is to get all the variables on one side and all of the constants on another. So my left-hand side is okay, but on my right-hand side, I'm going to want to distribute first, so that I don't have a parentheses and I have everything in terms. And then I'm going to collect like terms, so I'm going to subtract 6 from both sides. And I should already be, wait, something's up here, because this is telling me this is equal to this plus 2. But let's finish. Let's subtract 2x from both sides. So if I subtract 2x from both sides, take away 2x, I get 0. Take away 2x over here, I get 2. And so this simplifies to saying 0 is equal to 2. And that's false. So if I follow all the rules of mathematics, I'm assuming that this is true. But I follow my distribution property. I add and subtract to each side appropriately, and I get something that's false. This tells me there are no values of x. that make this true. And so we say the solution for x, well, it's going to be the null set, since there are no values that keep this true. Well, let's look at one more here. So I'm going to look at 4x plus 6 is equal to 6 times x plus 1 minus 2x. Okay, we're going to play the same game we did in the last one. I'm going to want to simplify this expression so that I have everything in individual terms. So 6x plus 6 minus 2x. I'm going to gather like terms. 4x plus 6 equals 4x plus 6. Well, I can already see something here. These two things are identical. So if I subtract 6 from both sides, I get 4x equals 4x. And now if I divide both sides by 4, I get x equals x. And if I subtract x from each side, I get 0 equals 0. And this is true. And this is always true. And so this tells me no matter what value of x I have, this will be true. And so we say that x has the solution set of all real numbers. All right, let's work our way through some examples and just see all the differences we can see. One of the things we're going to want to do is we're going to want to check our answers when we can. So let's start with x minus 7 equals 3. So I want to focus on getting x. So the negative 7 is in my way, so I'm going to reverse it. I'm going to do its inverse. I'm going to add 7 to it. Now notice negative 7 plus 7 is 0, which leaves me with my identity for x. But to keep this equality true, whatever I did to one side, I have to do to the other. So I have x equals 10. Well, let's double check that. I'll put 10 back into the original for x. 10 minus 7 is 3. 3 equals 3. And this is true. That's what I wanted. I wanted a truth. So x plus 5 equals negative 12. Again, we want to focus on x, so we have to ask ourselves, well, what's in the way of getting x on its own? Well, it's an addition. So I will do the opposite. I will subtract 5. 5 minus 5 is 0, so that gets rid of that, isolating the x. But whatever I do to one side, I have to do to the other. And so since I subtracted 5 here, I have to subtract 5 here. So x equals negative 20. So I'll come back in and check. Negative 20 plus 5. And so negative 20 plus 5. And this is true. And so this is my solution set. X is equal to negative 20. So we'll have x divided by 3 equals 4. Now there's a couple ways I can look at a fraction. I can look at it as a proportion, and I can think of this as x divided by 3 equals 4 over 1. And a common way of approaching that is to cross multiply. I can also look at this as a division, x divided by 3. And so if I want to undo a division, then I'm going to want to multiply. And I want to do it both ways. So over here I'll cross multiply, and here I'll look at it as a division. So to undo this division, I multiply this side by 3. But whatever I do to one side, I do to the other. And so 3 times x over 3, these will become a 1. And 4 times 3 is 12. And so x equals 12. I'll put it back into my original. 12 divided by 3 equals 4. 4 equals 4. And this was true. And so x equals 12 is my solution set. Well, let's look at cross multiplication. Cross multiplication says if I multiply down this way, I get one side, and if I multiply up this way, I get another side. When I have two fractions equal to other, they have to be fractions, no other terms, just fractions. And I got the same place. And I double check the same way. And this is true. Of course, we knew it was true because we did it over here, but it's nice to know that both of these techniques work for us. All right, let's look at some things where we have to do a little more work. Let's look at some distribution. So let's look at 23. So 5x minus 2x minus 10 is equal to 35. So I'm going to use this negative, and I'm going to distribute it. So 5x minus 2x, a negative distributed to a negative is plus 10, equals 35. I'm going to gather like terms. All right, I'm going to gather like terms. And so I'm going to have 7x, nope, not 7x, a 3x plus 10 equals 35. And now I'm going to subtract 10 from both sides. Subtract 10, subtract 10, 3x equals 25. And I'm going to divide by 3. So we get x is equal to 25 thirds. Or we could write this as what, 8 1/3? But I want to keep it this way. Well, we need to check this, and we're going to check it in our original. So 5 times 25 thirds minus 2 times 25 thirds minus 10 equals 35. So 5 times 25 is 125 thirds minus 50 thirds minus, well, what's 10 in thirds? That's 30 thirds, right? Equals 35. And so let's put all these together. So 125 thirds minus 20 thirds equals 35. I'll scroll up here. So 105 thirds is equal to 35. Well, let's do this division. 3 goes into 10 3 times, with 1 left over. 35 equals 35. It's true. And so there we go. We're able to check that. And so notice how we focus on the one side until we get x on its own. Right, x equals 25 thirds. And then we check it. We always check to make sure that we're maintaining our true value. All right, let's do some things on both sides of our equation now. So let's see here. Yeah, I'm going to do 33. Well, actually 35. 35, so 8y plus 2 is equal to 3y plus 4. Now here I have variables on both sides of the equation, so I kind of want to sort out my constants and my variables. But first I have to distribute to get rid of these parentheses. So 8y plus 16 equals 6y plus 8. So I've distributed these terms across. Now I'm going to bring my y's over this way by subtracting 6y from both sides. So I'm going to write out my next step. I'm going to say 8y plus 16. I'm going to leave a little space. 6y minus 6y plus 8. Right? I get rid of this to get rid of it. Right? Really quickly, it makes it go away because anything minus itself is 0. And so I've gotten it off this side, but if I do something to one side, I have to do the same thing to the other. So I'll collect like terms over here. And now I want to get rid of this 16. So 2y plus 16 minus 16 is equal to 8 minus 16. So that's negative 8. And I'll divide both sides by 2 now. y equals negative 4. Well, let's test that. So 8 times negative 4 plus 2 equals 2 times 3 times negative 4 plus 4. And so negative 4 plus 2 is negative 2. And let's see, 3 times negative 4 is negative 12. And so 8 times negative 2 is negative 16. And what is this? This is 2 times negative 8. Or negative 16 is equal to negative 16. Hey, it's true. And we check to make sure it was true. Alright, let's do some things that have fractions in them, and some things we can do to work with fractions in general. So let's look at 47. Room for 47? Yes, I do. So x divided by 3 plus x divided by 2. Now, I can do something to one side of an equation and it affects the other. And so there's a couple different ways to think about fractions. I'm going to focus on getting rid of the denominators one by one. So the first thing I'm going to do is I'm going to get rid of the 3 here. So if I were to multiply this term by 3, it would get rid of it. But that changes the value of just one term. So I'm going to multiply the whole side by 3. But if I multiply this side by 3, I have to multiply the other side of the equation by 3. So I'll distribute this. So the 3 times the 3, those will cancel. And this will give me 3x divided by 2. Right? So if I distribute the 3 times the 1 over x over 3, the 3's cancel, leaves me with x. And the 3 times x divided by 2 is 3x divided by 2. And those will simplify, leaving me with 5/2 on the right-hand side. But I still have another fraction. So what I'm going to do now is I'm going to multiply by 2. So that'll cancel this. But whatever I do to one side, I do to the other. So 2 to x, because I'm going to distribute. I'll distribute again. The 2's cancel. And now I'll combine like terms. And then I'll divide. Divide both sides by 5. And I get x equals 1. So I'm going to come back up here to my original equation, and I'm going to check. So I'm going to replace x with 1. I'm going to get a common denominator, so 2/6 plus 3/6, and that is 5/6 equals 5/6, so this is true. And so we're working our way through the different ways we can solve it. There's another way to look at this. If I have the x divided by 3, x divided by 2 equals 5/6, I could look for a common denominator. And I notice, hey, these all could have 6 as a common denominator. And so to get 6 as a common denominator, or to get rid of 6 as a common denominator, I'll multiply the whole equation by 6. So now I'm going to distribute this to each term in the equation. So 6 times x divided by 3 is 2x. 6 times x divided by 2 is 3x. And 6 times 5/6 is 5. And I'm at the same spot I was up here. Because the fractions don't always give a nice, quick to find common denominator, I don't mind peeling them off one by one. As long as I keep doing it to every term, I eventually get to where I need to be. All right, let's do a couple more here so we can see the various techniques we can bring to bear. All said and done, whatever I do to one side, I'm doing to the other. So let's look at some proportions here. In fact, I'll look at a more complicated proportion. I'm going to look at 71 in the textbook. So I have y plus 10 over 10 is equal to y minus 2 over 4. And so we're going to use cross multiplication. We're going to use that, when I have two fractions equal to each other, which is called a proportion, I can cross multiply. And so 10 times y minus 2 is equal to 4 times y plus 10. Why am I saying I can cross multiply? Let's take a little bit here to see why this is true. So if I do y plus 10 and y minus 2, if I say I want to get rid of the 4 on this side, so I'll multiply this side by 4. But whatever I do to one side, I do to the other. And if I want to get rid of 10 on this side, I'll multiply by 10. And so whatever I do to one side, I do to the other. So these 10s will eliminate, giving me 4 times the numerator. And these 4s will eliminate, giving me 10 times the numerator. And that's exactly what I got here. So once I've cross multiplied, I'm going to distribute. So 10y minus 20 is equal to 4y plus 40. I'm going to subtract 4y from both sides. So 6y minus 20 is equal to 40. I'm going to add 20 to this side, 6y. And so if I add 20 to this side, I'll add 20 to this side. And I'll divide both sides by 6. And now I want to test this in my original expressions. So 10 plus 10 over 10 is equal to 10 minus 2 over 4. So 10 plus 10 is 20 over 10, or 2 over 1. And 10 minus 2 is 8 over 4, or 2 over 1. And this is true. And so the concept of whatever we do to one side, we do to the other. And the idea of proportions help us solve equations. All right, that's all I have for now. Until again. Let me close this out for you guys.